So numerical weather prediction give us the meteorological variables we rely on to make forecasts of the weather. Here is a mean sea level pressure map coming from numerical weather prediction. In this case, it's from the Australia's Bureau of Meteorology's weather forecast system called ACCESS. So here's a mean sea level pressure from ACCESS for a given time. In reds, we have the highs, in blues, we have the lows. And I guess this is what comes out of the model, but it gets synthesized, or rather reduced, to these contour plots that perhaps you're more familiar with seeing, these synoptic charts, mean sea level pressure charts. In this case, the high over the southwest coast of Australia and Indian Southern Oceans, the lows across the continent here. There's a very intense low pressure system, then very intense low pressure system. In this case is a tropical cyclone Riley. And so this is just what people use to, or whether forecaster would use to look at the positioning of the high pressure systems, the movements of air masses, and how they might encounter each other. Just so this links back to some level of reality. On the left here, we have a satellite image of the system. This is from the Japanese meteorological satellite. It takes every 10 minutes a snapshot of the full disk of the Earth, what it sees in our region anyway. And the reason I've got it here is to demonstrate that some of these features, this band of cloud, the void of cloud here, matches up with the synoptic charts. These features that we see on weather maps actually correspond to real phenomena in our atmosphere. The band of clouds, the cold front moving in from the Southern Ocean, about to encounter the low pressure system. Remember, the low pressure system is that warm, dense, lifting air across the Australian wheat belt here, West Australian wheat belt. So yeah, my point here is really to link what we see from the mean sea level pressure analysis, these contour maps, linking them back to some level of reality as observed from our space satellites. And please, by all means, do go and avail yourself of the resource that we have at the Bureau of Meteorology. We're very lucky that within a very short time frame, we're able to access their mean sea level pressure analysis by going to their website. I suggest you'll check it out. And perhaps as a far nicer way than I could possibly do, they present this information in a way that's easily accessible, digestible, and perhaps even a little more interesting than I can deliver it. So anyway, the mean sea level pressure charts, they're characterized by these contours. They're called isobars. Isobars are lines of equal or constant pressure measured in hectopascals. Hectopascals is what I've come to learn as the measure of mean sea level pressure. A few years back, they used to be referred to as millibars. They are the same thing. Troughs are highlighted as these elongated areas. In this case, we have a trough forming off the, troughs, they're gullies, if you like, if you're thinking about topographic maps as an analog for these mean sea level pressure charts. Gullies, so the areas between two hills or two mounds as the troughs. So typically you'd see a low pressure trough across Australia. Fronts are identified by these lines with triangles on them. They can be warm or cold. In fact, the way they can be combinations of the two as well. And they also show the wind speed and direction. Now, remember, we talked about the contours, the spacing between the lines in the pressure charts. If they are close together, that means there's a steep gradient, and therefore the winds will move faster through that area compared to wider spacing between the lines. So here's an example of a cold front, large cold front bringing that cold air from the polar area onto the Australian continent, warmer air over the continent. As you can see, it's sort of heading in the direction of South Australia, Adelaide here, where there's a high pressure system. Now this high pressure system clockwise out of the high into the low, it's dragging warm air down from the continent. So when we look at the rain that this cold front generated, sure enough, it's in that area. It looks like it was about to get hit here. So we can sort of, we match these things up retrospectively to see if it makes sense. This is a chart, a map of daily rainfall from the Bureau of Meteorology. I suggest you get familiar with these data too. They'll be a great resource for your research in the future anyway. So yeah, that's linking the patterns we see in the mean sea level pressure analysis to the ultimate rainfall distribution we see across the country. Yeah, so it's the high pressure system and the low pressure system, the equalization or the movement of air between those two that moves air masses around. The air masses are characterized by their moisture and their heat, their moisture from which part of the ocean they come from, and the heat from which latitude they come from. Sorry, here's just another illustration that the flow is anti-clockwise or deflection to the left out of the high. It follows the contour lines because it's further south. Coriolis is kicking in, so you get the long features. You get the flow that's almost geostrophic going into the low pressure system here. So the movement of air is along the contour here, pushing this cold front onto the continental air mass and ultimately resulting in rain that we see here. So become familiar with these contour maps, understand that the lower in the on the Earth's surface, the higher latitudes, we call them, you'll get the persistent, the long range pressure systems, the spread out pressure systems, and that we follow them to the anti-clockwise, counterclockwise out of the high, and clockwise into the lows. And so here we have the wind or the air's being cold front moving onto the Australian continent. So an analysis of the mean sea level pressure, we can explore some of weather phenomena we get in the region. And one of the examples of severe weather we cop in Southeast Australia particularly is known as the East Coast lows. Now this is an area off the coast with a very strong low pressure system. So if we saw that on a contour map or the mean sea level pressure map, very tight isobars around a low pressure system. And so that means very strong winds. This particular system parks itself south of Queensland, north of New South Wales, or to the east of Victoria. So they're typically found off the east coast. It's one of those features of Australian weather that can intensify overnight and lead to some catastrophic. And it's characterised by strong winds, large ocean swells, and heavy rainfall. And they occur mostly in autumn and winter, with greatest intensity around June. So here's just a couple of examples of the consequence of East Coast low. Back in 2007, the Pasha Bulker, a bulk carrier, was hit by one of these systems. The Newcastle and the surrounding areas, lots of storm damage, devastated the area. And this ship ran aground on Nobby's Beach in Newcastle in June. It was a consequence of East Coast low. So too more recently, this storm of Gullies. Now, when we look at the system and how this is the Gullies example here. So what you have over a sequence of days leading up to the thing, leading up to an East Coast low, is the formation. So it starts off with this trough. This is a low pressure trough. Trough is the region between these two highs over here. Now that trough starts to intensify as a low pressure system the following day, the 19th of June. That eventually starts to come down the coast, the trough and the low pressure system intensifying, the contour lines getting tighter and tighter until eventually they're very tight contour in the low pressure system here. The high winds are coming in off the high pressure system here into the low moist air, lots of rain, lots of damage. So too for more recently, earlier this year, we had a East Coast low. Again, watching the formation of the low pressure system through the sequence of mean sea level pressure charts, we can see the trough that forms over the east coast of Australia, extending right across from north to south, intensifying to eventually being this elongated trough here, drawing a lot of moisture and wind from the high pressure systems around it. Oops.